Good morning. Here we are. It's the physics video lecture. Physics 105A video lecture 12. We're talking about harmonic oscillations. This time I'm going to set up a couple of systems and we'll work on those. They're interesting systems, by the way. So let's start with our formalism. Harmonic oscillations result when we have a potential energy ½ kx squared. Okay, and the upshot of that is that our motion, which is from mass times acceleration equals minus kx, which is what we had last time, right? We have x equals a cosine omega t plus some phase constant alpha. A is the amplitude. Omega squared is equal to k over m. Okay. So we've been studying that. We have the period is, and I'll put this here, since t is equal to 2 pi divided by omega, we see that the frequency and the period are completely amplitude independent. Okay. Good. So what are the systems we want to look at? So here's some systems. The first one, we'll just take the generic mass on a spring. You guys probably remember the idea is that we have a mass on some kind of frictionless track here. So there's m and there's k. And we could have an x equals 0 here, and then thing oscillates back and forth. Okay, no friction, oscillates forever, and there, of course, is the law of what's going on. So we want to just name this number 1. The second one, we're going to add something to it. We're going to take this same spring labeled K and the same mass, and we're going to hang them vertically. So that we represent by this scenario here. And we'll even still have the positive x-axis there. But what now is the potential energy? So in this case, U of x has a gravitational potential energy component. We'll say mgx, and it has a spring, right? An elastic, if you want to call it that, potential energy component. So plus 1/2 kx squared. Of course, we could add an arbitrary constant. What I've done here is I've assumed that the origin, I'll just call it right here, I've assumed that the origin is the point at which the spring is completely relaxed. So if you had the mass, you would hold it here and then you'd let go of it gently and it stretches the spring. But there's our potential energy. Now, what was this K really? This K was the second derivative of the potential energy. So recall, K is actually equal to U double prime of x0, where x0 is the equilibrium position. In my case, I could say, okay, this was the unstretched length, and now I'm going to say that this here is x0, since the thing's not in motion, so it's an equilibrium there. Now the idea is I pull down on it, it bobs up and down. Good. So what we're going to do is do our differentiation on this function and see what happens. And this is quickly done. Differentiating equation star. I always name everything star. Well, I can't reach that. I go ahead and name it star. Differentiating equation star. Well, for the record, let it be done. Here we go. Equation star. We have u prime of x is equal to mg plus differentiating x squared, we get 2, cancels the 1/2, so mg plus kx. Now, the equilibrium position is found when x prime or u prime is equal to 0. So u prime of x0 equals 0, comma, when x0 is equal to, we're just setting this equal to 0 here, minus mg divided by k. That's just the equilibrium position for mg, the force down, kx, the force up. Good, so we have that. What about our second derivative? U second derivative, evaluate, well, get the x0 for the moment. U second derivative of x is equal to k. And what do we learn from this? Twofold. Therefore, the frequency of oscillations is not affected by that gravitational field. So this is the lesson here. The oscillation frequency is left unaffected by a constant field, by a constant force. So it's not affected by the constant force, and that's exactly what that is. The weight is a constant force. By the constant force. And the other thing that we learned is that we've just shifted the origin. We've actually seen that before. This x0, this equilibrium position, has just been shifted. So that's what a constant force does to a harmonic oscillating system. It just shifts the origin. Which merely shifts the origin. We'll leave it like that. Merely which shifts the origin. So that's what it does do. Constant force shifts the origin. I'll kind of underline that. Constant force shifts the origin, leaves the frequency unchanged. And you'll notice we didn't end up with a different K, right? There's our definition of K, but the spring system was already labeled K. Now our next system is a generalization, or actually just a slightly different spring system. This one's really good. 1, 2, 3. Okay. This one I'll get started for you guys and we'll work on together. You guys can do it for a homework. Let's just call this 2 springs. And these 2 springs are going to be hooked up in a special way. So here's our mass, and this is a top view, so we're looking down on the mass, and I'll kind of do a dotted line for the x-axis. And the way we're going to attach these springs is we're going to hook them to either side of the mass and then attach them to a fixed frame of some sort. So we're looking at a top view, and you guys can see what we're driving at here. We pull this thing out to the right, and it oscillates back and forth. Okay. So each of these springs has the spring constant K, if you just took the thing off the shelf. But we have to make a note about this. It's a spring of unstretched length L. Unstretched length L. And spring constant K, I'll just put that here as redundant. But what we've done is we've put it in a frame here where we're going to have a length A on both sides. So this is geometrically, this is our device here, that's the length A. And note, A is greater than or equal to L. A is greater than or equal to L, so if we take the case where A is greater, we actually hook these things up and have to stretch them both a bit. So it's under tension right now, it's under equal and opposite tension. So we want to find the potential energy. So find U of X for this system. I'm going to keep drawing on this, by the way. So this is a sketch you want to have be large enough. So imagine we stretched this thing out to here. And our spring goes like this now. Okay. We've stretched it out to there. How much, and this M is now at position we'll label X. So there's the position X. So how much potential energy is in that system? The springs have been stretched. For that, we need the Pythagorean Theorem, apparently, because the energy in a spring is a half K times the amount that's been stretched squared. Let's see what that gives us. I'm going to find U of X. The thing has been constructed symmetrically, so we'll put a 2 in front of it, so we'll have U of X is equal to 2 times 1/2 K, and let me just write now delta X squared, how much it's been stretched. But that's what we have to determine. And it's good to keep the 1/2 out front, and then we just have these 2 K's together like that. But what about that delta X squared? There we have to say, what is the length of the hypotenuse minus L? So I barely do that. A is greater than or equal to L. So L is the length of the spring. So the hypotenuse is A squared plus X squared, square root of A squared plus X squared. That's the frame there. A squared plus X squared. And we have to subtract off L, which is the original length. So that's how much the spring has been stretched. A squared of A squared plus X squared. A is here, X is there as a hypotenuse, minus L. So this is our function. And now I'm not sure if I'm just going to keep working it or hand it over to you guys. This is, yeah, can say a couple words about it for sure. So what we're looking for is the second derivative. We need u double prime at x0, but x0 is clearly the origin. So first, if we just think about this function a bit, what does it do? It's symmetric. Let's go ahead and try to graph it before we do anything. It's clearly symmetric, and when x is equal to 0, it's root a squared minus L. Okay. So that's root a squared, which is just to say a is a positive number. So it's a minus L, so it's 1/2 2k a minus L squared. Okay, I said it. You guys write that down a little nicer. Point is, it's non-zero, and this is a symmetric function with a local minimum. Here, I'm just gonna point it out. It's a symmetric function with a local minimum. Okay. Now, there's an interesting property to this that you guys can discover mathematically. So what you're going to do is take two derivatives, and that'll be your effective k equals the effective spring constant of this thing here. Effective, I'll write it out, k effective, okay. But if A is equal to L, and you can't just see this by, by inspection, but if A is equal to L, so if you have the equality and not the greater than, then the second derivative actually vanishes, and you no longer have harmonic oscillations. So this is a pretty rich system, because it's only when the second derivative is non-zero, positive, that you have the harmonic oscillations. So I'll go ahead and call this a homework. Make sure you agree with this construction here, and then find u double prime of 0. That's k effective, and from that you get the frequency of I'll just write omega of harmonic oscillations. And I'll also write, and this will follow immediately. Show that u double prime of 0 equals 0, comma, when L is equal to A. But what that's going to leave us with is the interesting question: what kind of oscillations do we have if the second derivative is 0? And I'll even write something about that. Because this function has its minimum at x equals 0, let's write down what the Taylor expansion will be like. So the Taylor expansion, I'm going to go ahead and leave this picture up, that's good. First of all, just write out several terms. So u of x is equal to u of 0 plus u prime of 0 x plus 1/2 u double prime of 0 x squared. And of course, that's your homework assignment, right? Plus 1/3 factorial third derivative at 0, x cubed. And let's just keep going for a couple more. Fourth derivative at 0, x to the fourth, 5 factorial, fifth derivative of 0, x to the fifth. And we can keep going on. This thing will actually generate an infinite series. So this is a constant, right? Now for our function, u prime of 0, and you're going to find that. By the way, of course, you have to do, at the second derivative, you have to do the first derivative, and you're going to see it vanishes at x equals 0. So, boom, got that. This is going to go to 0. Now suppose this one goes to 0 as well, as it does in that particular case. What's going to happen with the third derivative? Well, the third derivative is going to have to vanish because this is clearly an even function, right? The construction gives us an even function there. So the third derivative will vanish as well when the second derivative vanishes. And the next term will actually be the next non-zero one, would be the fourth derivative. We may save that assignment for later. But yeah, the next non-zero one would be the fourth derivative. So in this, and then this one again, because we have an even function there, this one's going to vanish. So this is going to be the first term that plays a role in the dynamics if, you know, if we have this situation when L is equal to A. So that's an interesting note here. So note for L equals A, u of x is approximated by 1 over 4 factorial fourth derivative at 0 x to the fourth. And now I'm going to remind you of those potentials we had the other day where we've taken x even to the nth power. Okay. So this is a time to return to those and talk a bit about them. So yeah, for the homework we're just doing this for now, but keep this in mind because we may add that to the mix later on. It's a little tedious to do 4 derivatives of this thing, but it's not the end of the world either. Let me just salt the clock. Okay, very nice. Good, yeah, so far, go ahead and when you write this out, make sure you show the construction and also that it all makes sense. You're just working your way to there. And in fact, you may want to just include this commentary here. Our next system, okay, so we've come up to this point here. We want to characterize these higher powers once again. I had done something in the past with the period of oscillations, and now we've learned a bit more. So we are returning to that. Good. For one thing, what we've done is we've generated a system, we've constructed a system that has an x to the fourth potential. So let's return to recall when I had u of x is equal to b x to the nth power. And we're just going to have n greater than 0 right now. So I'm going to draw a nice sized graph here, x, u of x, and let's go ahead and I'll do a bunch of dotted lines. There's our n equals 1, I'm just going to have units where b is equal to 1, okay? That way we can keep this simple. And then because that way these all intersect in the same place here. So here we would have the parabola for n equals 2. Should have made this more symmetric, but you get the idea. I'll just work on the right side here. Yeah, so the parabola for n equals 2. And then n equals 3, since we're taking the absolute value, it always gets flatter and flatter. So n equals 4 I'll do, and just it's flatter and flatter at the bottom and steeper as you go up. These are the potentials that had amplitude-dependent periods, therefore also frequencies. So it's only that n equals 2 that has the amplitude-independent frequency. And that's what's characterizing harmonic oscillations. So this one here is my n equals 4. You should play around with numbers a little bit to make sure you recognize what's going on here. If you're out at 1/2, then 1/2 squared is a quarter, right? 1/2 to the 4th is a 16th. So it keeps all the way out, it keeps being flatter and flatter. If you take that limit, n goes towards infinity, you can arbitrarily closely approximate a square well. Like that. So I'll put that as a note. N goes towards infinity. Or how about large N approximate a square well? A square well potential. Take n to infinity, this will be arbitrarily flat all the way out to arbitrarily close to 1 and then shoot straight up. And so that's a square well potential. Let's draw the square well potential. So now we go out to minus a, and we have this, basically, what we say for a square well, u of x, is that the potential is constant, we could say equal to 0 between minus a, and it's infinity outside, so a particle is forbidden to have any amplitude greater than a. Let's say something about this. So square well potential. You often write it this way. You say u of x equals 0 for x less than, say, a. Okay. And it's infinity for x greater than a. And the fact that we don't have equality here means what we're thinking of is infinitely steep segments going up there. So that's the way to discuss the square well potential. And you can see this in the limit as n goes to infinity is just that, okay, very square. Okay, so what is the dynamics of a particle in a square well? It's actually trivial. A particle in a square well potential. Square well potential. It's a free particle. What it's doing is it's just drifting over. When it hits the wall, it reverses direction and drifts back. Okay. You can think of it, it's like an elastic collision with a completely massive and elastic wall, and otherwise it's just going back and forth. So that's the dynamics. They're trivial. They're constant velocity with reversing of direction. Do the question mark. So trivial in that regard, and we can do the following. We can say V naught T is equal to what? Well, if T is going to be the period of this back and forth oscillatory motion, it's going to have to be equal to 4 times A. So from A to minus A and back again. So V naught T is equal to 4 times A. T is equal to 4A divided by V naught. But okay, since we're talking about a particle mass m bouncing around in there, there's also an energy involved. So what is the energy? I have room right here. I'll send this up here. So for the energy, we have to have E is just 1/2 m v naught squared, because the thing is free almost all the time, and then it's just drifting back and forth. So it's just purely kinetic energy, f m v naught squared. And so yeah, the energy can also be related to the period and the amplitude, okay? Because you could solve for V naught, which would be 4A over T, and then 1/2 m 4A over T quantity squared would be your energy. Finally, let me consult the clock again. I have a good problem to wrap this up. Okay, great. Now let's go back to period of oscillation in the potential U equals B x to the nth power. So we had that we have that in our notes. We'll just write it down again. Just to remind you, we get that from 1/2 m dx dt squared plus U is equal to E. In this case, we have E equals B A to the n, and T was equal to, do I remember this? Leave a little space right there. We're going to go 0 to A dx root 2 over m, and then the energy B A to the n minus B x to the n, because we're just going in the right hand side there, and so we need 4 of these. So here's a really interesting homework problem, is to show that this period here is going to be equal to this one up here, okay? So this period here is going to be equal to this one up here in the limit as n goes to infinity. Good, so everything's in place. We got this star, and we have double star right here. It's 4A over B0. Show that T double star equals T sub star in the limit as n goes to infinity. You'll find in your notes how I turn this into a dimensionless integral And so what you can use is, you may use integral 0 to 1 dx over root 1 minus x to the n. What does that go to in the limit as n goes to infinity? This becomes negligible everywhere except at the very corners of the thing. So this integral itself just goes to 1. Proof of that is a little more challenging. We're just going to use it. Maybe we'll come back to the proof later. I like to show everything. But for the moment, we'll just make use of that. And you have to make use of that, and very important, at some point in the problem, you're going to make use of this as a second substitution. Okay. So after you've turned this into a dimensionless integral, you pulled everything out front, you put e back in there in this form, and that gets rid of all of your n going to infinity term. Okay. That's how. So you make a substitution with this before you take the limit n goes to infinity. And the limit n goes to infinity is really just working on this integral and making use of this fact. So that is really an interesting problem, because we've got the basic formalism for period of oscillations, right, in an x to the n or x linear squared, etc., x to the n potential well. I mean, you could just imagine things rolling back and forth. And in that limit where it becomes infinitely steep, it just has to turn into a ball bouncing back and forth. So when you see this come out, it's pretty satisfying. I think that's a good place. It is indeed. So that's where we'll stop for this time. This is also a homework problem. Did I write that here anywhere? Yeah, it's right here, homework. Good problem. That, and then that other system with the springs, we get some really nice results on these. And there's interesting math involved as well. So something for everybody. Good, enjoy these problems, and we'll see you guys next time.